As we all know, once the basic behavior of a device, and in this case diode, is understood, then its responses in a variety of configurations can be examined. Like in the earlier lectures, we discussed the n-type materials, p-type materials. We got the concept of doping, the forward biased, reverse biased. So in this lecture and even in the next few lectures, we will discuss the applications of diodes. The analysis of electronic circuits can follow one of the two paths. One is to analyze the actual characteristics, or the second one is to apply the approximate model for the device. In the actual diode characteristics, we shall utilize the Shockley's equation, which is an approach to identify the variables by implementing nonlinear mathematical techniques, and which we will definitely discuss in the lecture, but not in detail. And in the second case, we shall discuss the load line analysis, which is the core topic of this lecture. In the approximate model, there are three possible techniques. One is the piecewise linear model, the second one is simplified model, and the third one is ideal diode model. Okay, first coming to the nonlinear mathematical techniques. On the right hand side, the right side of the figure, you can see there is a voltage source, which is denoted by E, and there is a diode, which is D, represented by D, and one is the resistor. So we can see all the elements are connected in series, so it means that current will not divide and only a single current will flow throughout the circuit. So from the KVL, we can assume that we can say that there is a rise in potential here, which is called E, and there are two drops. One drop is across the diode, whereas the second drop is across the resistor. The diode drop can be represented with VD, which is voltage drop across the diode, whereas the voltage drop across resistance can be represented by VR, means voltage across the resistor. Using Ohm's law, we can simply write the rise in potential must be equal to drop in potential. So E is the rise in potential, and VD and VR are the drop in potential. So rise in potential is E is equal to drop in potential, which is VD, and drop in potential, which is VR. Or Ohm's law is also stated like rise in potential plus drop in potential must be equal to 0, or summation of all the voltages must be equal to 0. This is called Ohm's law. So just putting the value of VR in this equation, which is E is equal to VD plus VR is equal to VD. We don't know about VD plus ID into R. I is the current which passes through a diode, and R is the resistance of a circuit. So one of the unknown. So we'll just identify the current ID, which is ID is equal to E minus VD divided by R. This is the maximum current which flows through this circuit and through the diode. From the Shockley's equation, we can also write the nonlinear equation, which is we can find out the nonlinear equation for a current ID, which is ID is equal to IS e power VD by NVT minus 1. So we can also find out the ID current directly from the Shockley's equation. Before discussing the load line analysis, which is the main topic of today's lecture, it's better to just take a review of the other three techniques. Starting from piecewise linear model, considering the circuit on the right side is the same circuit which we discussed earlier for the nonlinear model. It's a rise in potential represented by E, and the drop in potential, this thing which is the resistor plus ideal diode. We'll discuss shortly about why the diode is replaced with this combination of ideal diode plus resistor. And the third one is resistor. The drop across resistor R is VR, same like the previous diagram. So in this model, we have replaced the diode with a combination of a resistor, which shows the internal resistance of a diode, and a ideal diode. So these two elements, when combined, it results in the original diode. So applying the same KVL equation, rise in potential plus is equal to drop in potential, or summation of all the potentials are equal to 0. So E is equal to which is rise, is equal to Vd is a drop plus Vr is also a drop. So E is equal to Vd plus Vr, and just write the equation of values of Vd and Vr. In case of Vd, we know there is current Id will flow, and the internal resistance of our diode is R of DC. So it's Id RDC plus the drop across the resistor R, which is VR, is equal to Id into R. As we knew that the same current will flow from this diode and the resistor R, so both currents are represented by Id, which are called the diode currents. Okay, from this equation we can easily find out Id, which is equal to E divided by RDC plus R. From this equation we can identify the current flow in this circuit, or the current through diode, or how much current it will flow from the diode. So the only thing which we need to know prior to use this linear model is we must have a knowledge of Q point to find the RDC. We must know the value of RDC, which can be seen from the data sheet. In the other two models, which are simplified and the ideal model, in the simplified model we replaced the diode with the drop of 0.7 volts. As we are using the silicon diode, so the drop is 0.7 volt, and if we change the diode to germanium, then the drop will be 0.3 volts. So writing the KVL, applying the KVL on this circuit, and the equation will be rise in potential is equal to drop in potential, or summation of all the potentials are equal to 0. So E is equal to Vd plus Vr, where Vd is equal to 0.7. the drop we already knew that it's 0.7, plus the drop in resistor is Id into R. Let me take out the pointer. Okay, so from this equation we can easily find out the value of Id, which is Id is equal to E minus 0.7 divided by R. So for this one, the simplified model, we must know the value of E, which is the potential, and we must know the value of R, which is the resistor in the circuit. So in case of ideal model, there is no drop basically, and the equation will be E is equal to VR. It simply shows that this is the rise, and the whole voltage will be dropped here. So rise in potential is equal to drop in potential. There is no drop here at this stage, because the ideal diode, when the zero potential or 0 volt will be applied here at this end, and diode will allow the current to pass through it. So E is equal to VR, and by putting the value of VR, E is equal to IDR, and from here we can easily find out the value of ID, which is ID is equal to E by R. Okay, coming to the load line analysis, which is a graphical method. Before coming to this circuit, let me explain this plot, which is the plot between VD, voltage across the diode, and the current ID, the current through the diode. So this is a standard equation at 0.7 volt. Let me write here. It's very difficult to write here, but let me try 0.7. Okay, it's not very good, but okay. Around 0.7 volt in case of silicon, you can see that the maximum current will flow. Let this stage, let me write here, let this is 0.3. At 0.3 the current flow across the diode will be like this. It is in milliampere, but let it is for example it is 1 milliampere. Okay, at 0.3 or 0.2, just an example, I write here 1 milliampere, but at 0.7 volts maximum current will flow through a diode. So this is a 2D plot. In 2D plot I have shown you the voltage. When the voltage of 0.7 will be applied to the diode, it will it will allow the current to pass through it and maximum current to fall through. So can you see the curve? There is a curve here. So if you keep on increasing the voltage until 0.7 threshold voltage is achieved, just see that the current is increasing gradually. Okay, coming to the figure, it's the same figure which we discussed earlier, that there is a rise in potential. It's a series combination. There is a rise in potential which is called E, and there are two drops. One is across the diode and the second one is across the resistor. So summation of all the voltages must be equal to 0. So rise in potential is equal to drop in potential. Drop here D1 and drop here D2. Drop 2. Okay. So coming to this circuit, okay, as we all know, in the horizontal axis, which is the VD axis, and this is a standard equation which we got from here, E is equal to VD plus IDR. IDR means VR, so we just put the value of VR here, which is IDR. So this is after applying the KVL, E is equal to VD plus IDR. So coming to the horizontal axis, when VD is 0, when VD is 0 means at this point, so VD is 0, when VD is 0, then the equation will be E is equal to ID into R, or ID is equal to E by R. So when VD is 0, I is equal to E by R. So putting here I is equal to E by R, and this is where VD is equal to 0. So in the vertical axis we got one point which is E by R, and at E by R the horizontal axis value variable, which is VD, it is equal to 0. Now apply the same approach by following the same approach on equation number 1, that E is equal to VD plus IDR, but let ID is equal to 0, means horizontal value equal to 0. Then we will go to the vertical value is equal to 0, then we only have the horizontal values. So E is equal to 0, E is equal to VD plus 0 into R. So E is equal to VD, so we'll write here E is equal to VD. We just put another variable E, which is the potential. The value of E can be written here. Let VE is equal to 10 volts. We just point out the value here, which is, let, for example, in this case is equal to 10 volts. So what we need to do, we must know about the actual plot. Like in this case, this is a silicon plot, and this plot we can get this plot from the from the data sheet. That now we have vertical point, which is E by R. We have horizontal point, which is E. What we need to do, we need to connect these 2 points with a line, which is the load line. And you can observe here, there is a cross section here at this point, which is called the Q point. So what we must have before plotting this line, we must know the vertical value, which in this case is E by R. If we have some values, let E is equal to 10 volts, R is equal to 2 ohms, then this value will be 5. And we must have the horizontal value, which in this case is E. So we have combined, we connect these 2 points, and we also know the characteristics of the diode which we are using here. So the characteristics of the diode is, the line is this one, and the point where the load line cross the characteristics curve is called the Q point. So the vertical point, the vertical line shows the value of IDQ, whereas the horizontal cut shows the value of VDQ. So we have obtained IDQ value, which is this one. We have also find out the VD value, which is VDQ, from this plot. Coming to example 2.1, in which we have a series combination, which is figure 2.3a, and on the right side we have a characteristic curve of a diode, which is 2.3b. So what we need to find is a VDQ and IDQ, which we shall find using the load line analysis and the voltage across the resistor, which is VR. So from this circuit we can write the equation after applying the KVL. E is equal to VD plus VR, and by putting the value of VR, which is E is equal to VD plus IDR. So when the VD is 0, we'll be getting the vertical value, and when ID is equal to 0, we'll be getting the horizontal value. So from here you can see the equation, ID is equal to E by R, and where VD is equal to 0, just put this value is equal to 0, then ID is equal to E divided by R, and we'll get E divided by R here somewhere, E by R. And similarly at the horizontal axis we have current value, ID is equal to 0, so E is equal to VD. So E is equal to VD, so just put the value of E here. So ID is equal to E by R, and E is given, it is 10 volts, and the R is given, which is 0.5 kilo ohms. So we'll be getting the current 20 milliampere. So this is the point where ID point. Okay. Whereas in the second case, VT is equal to E, so just insert the value of 10 here. It will be around somewhere here. Okay, in the next figure we'll be getting the value. So we got 2 points, one on the horizontal value, horizontal axis, whereas the second point is on the first point is on the vertical axis, whereas the second point is along the horizontal line and the horizontal axis. So the horizontal value is 10 somewhere here, whereas the vertical value is here, which is 20 milliampere. So from here we got, and this line intersects the characteristic curve at this point. This is called the Q point. So the value here is around 0.78, as it is given, 0.78 volts, whereas the value here is it is right, it is 18.5 milliampere, approximately equal to 18.5 milliampere. So with the load line analysis, we got two values. One is VDQ, whereas the second one is IDQ. Okay, in the second case, we need to find the VR, and VR is the drop across the resistor, and we knew that the rise in potential is 10. First drop is 0.7, whereas this is 0.7, and from here 0.78 basically, and the second drop we need to find is, so from the same equation, E is equal to VD plus VR, and VR is equal to E minus VD. E minus VD, E is given, which is 10 volts, whereas VD we have already calculated, which is 0.78 volts. So 10 minus 0.78 volts is equal to 9.22 volts. So out of 10, 9.22 volts will drop here, whereas the 0.78 volts will drop across the diode. Okay, so this is the complete figure where E value is 10 volts on the horizontal axis, whereas on the vertical axis the value is 20. So we connected two points using a load line, and where this line intersects the characteristics curve, this is called a Q point, and the value here is 18.5 milliampere for the IDQ, and for the voltage the value is 0.78 volts, approximately equal to. So using the Q point value, the DC resistance, for example, can be calculated as RD is equal to VDQ by IDQ, where VDQ we have already calculated is equal to 0.78 volts. Where is the, okay, and whereas the IDQ value we have already calculated, it's 18.5 milliampere. So the resistance is 42.16, and here it is the resistance of 42.16 ohm. Like now we have all the resistance values. Now we can also calculate ID. ID is equal to E by summation of R. This is called the Ohm's law. So E is already given, which is 10 volts, whereas summation of R is 42.16 plus 500 ohms. So 10 divided by 42.16 plus 500 ohms is equal to 18.5 milliampere. It's the same value which we have calculated using the load line analysis. Similarly, the voltage drop, we can find out the voltage drop by employing the voltage divider rule, which is source voltage multiplied by the resistance value of the element where we need to calculate the drop, and summation of all the resistances. So VR is equal to E, which is 10 volts, multiplied by R, the resistance value, divided by summation of all the resistances, which is RT plus R. So 500 to 10 divided by 42.16 plus 500, it is 9.22 volts. So 9.22 volts will be dropped here, and the rest of the value, which is 0.78, will be dropped here. So it's the same value which we calculated using the load line analysis. Okay, we'll repeat the example 2.1 using the approximate equivalent model of the silicon semiconductor diode. Again, the circuit figure is redrawn, where the only difference here is this characteristic curve, which in case of ideal, which is under the ideal case, it's a straight line at 0.7 volts. It will allow the maximum current flows through it. So we already knew the value or vertical axis value of ID, which is 20 milliampere, whereas the horizontal value is 10 volts. So we connected these 2 points and found the Q point. It's the point where the load line intersects with the characteristic curve. So it's the value is around 18.5 milliampere. It's the same value which we have seen in the previous example. So there is not much difference here. The only difference is it has a straight line here. Like at 0.7 volt it will allow the maximum current, whereas at 0.6 volt or 0.5 volt, less than 0.7 volt, the current is straight away equal to 0. It can be seen from here. So VDQ is equal to 0.7 volt and IDQ is equal to 18.5 milliampere, and the result are somehow same like the previous example. Now in the example 2.3 we repeat example 2.1 using the ideal diode. In case of ideal diode at 0 volt, it will allow the maximum current flows through it. So here is the characteristic of ideal diode. So it's at IDQ is equal to 20 milliampere. We connected 2 lines, but this load line intersect with the characteristic line at 20 milliampere. So VDQ is equal to 0 volt, whereas IDQ is equal to 20 milliampere. Okay, this is the end of the lecture, and hopefully you have you got the basic concept how the diode can be used in the circuit and how we can calculate the value, current value, voltage value and the current value using the load line analysis.